I have a couple announcements, and then I will introduce Deshika. Please take a moment to silence your cell phones for whomever's just went off. That was perfect timing. We do have 2 lectures remaining for this winter season, Wednesday, March 25th, and then Wednesday, April 1st. The details to that will be on the back of your program. They will be here in Flug, and if you haven't RSVP'd, please do so. You can find that information on our website. This lecture will be filmed for educational purposes, and I think that's everything I have. Thank you again for joining us, and I will hand it over to our host for this evening, Deshika.
Thank you. My name is Deshika Narayanan. I'm an associate professor of astronomy at the University of Florida. I've been coming here to the center for like 20 years for conferences. It's a good place for getting like innovative ideas and space to think in the mountains, etc. So I am excited to introduce Rachel Bezanson as our public speaker today. So we're hosting a conference on the very first galaxies of the universe. And so we chose Rachel to give the talk. And Rachel's amazing. I mean, she's an observational astronomer, a professor at the University of Pittsburgh. She did her undergraduate work at Barnard College, her PhD at Yale. She was a Hubble postdoctoral fellow, which is like it's the best one. And at the University of Arizona. That's where we first met. And then she went on to be a Russell Fellow at Princeton, right? She's the PI of major projects like JWST, or co-PI of JWST Uncover. She has all these awards, right? Like Cottrell Fellowship and NSF Career, and that stuff is great, right? And if I kept going down, you would be like, yes, of course, Rachel's brilliant. But what makes Rachel awesome is just like how fun it is to work with her. She's a great person to work with. So I've been working with Rachel for like 10, 15 years.
Yep.
And I consider myself lucky to get, I mean, there's probably on this stage, you get a lot of folks who would not be that great to work with. And I'm sure, right? And Rachel's not. She's the kind of person who makes you feel good about yourself and your contributions to a collaboration. You can see it in her mentorship of the junior colleagues on our calls, and in her patience. Like, I'm 5 years late on deliverables and a grant that we have together, 6, and she hasn't bugged me about it. And of course, she brings brilliance to her collaborations. I think you're in for a treat tonight. When we had to pick a public speaker, we just all unanimously picked Rachel. It was not hard. We wanted someone who we knew would be exciting and for whom this would be easy. And you're going to see how awesome she is. So please join me in welcoming Rachel. I don't know how to turn that off, so it's just there.
I don't either, but it's fine. I don't know how many PhDs it takes to turn off a microphone, but it's more than 2. Well, thank you. I don't know how to follow that, Deshika, so I will just power on. It is my great pleasure to be here back in Aspen, back in Colorado, where I grew up, not in Aspen, but in Jamestown, Colorado, in the mountains of outside of Boulder. So my heart is in the mountains. And today I'm going to talk about giants, not 14ers nearby. But actually, these are spectra from the James Webb Space Telescope of some of the most massive galaxies in the early universe. And I'm going to talk about what we've learned in the kind of whirlwind of the last few years with the James Webb Space Telescope. And hopefully I give you a little bit of things that you want in this talk. But I'm going to start really with some bare bones. When we talk about galaxies, this is our galaxy, this is the Milky Way. You're here somewhere in the outskirts, maybe in the suburbs of the Milky Way. The Milky Way is really big, and galaxies are the things that include all of the normal stuff that you're used to. Stars and gas and black holes, which I consider normal, but probably shouldn't. Planets, people, aliens maybe. And then all the stuff that is not normal, like dark matter. That all lives inside of, or maybe galaxies live inside of dark matter. Galaxies are really big. It would take you 75,000 years traveling at the speed of light to get to the edge of the Milky Way, even though the Milky Way doesn't have an edge. Galaxies are big in that they are massive. So there are something like 5 with 10 zeros times the mass of the sun in the Milky Way. It's really big. That's just in the normal stuff. There's 20 times more dark matter in the Milky Way. But I'm not talking about galaxies like the Milky Way today. Today I'm going to talk about the really big things. Today I'm going to talk about the most massive galaxies in the universe. This is M87. M87 may look slightly less exciting, but this is a kind of one person's beauty is in the eye of beholder situation. So this is M87. It's a huge galaxy in the center of the nearby Virgo cluster. Inside of M87, even if you don't recognize this picture, you might actually recognize this picture. So this is an image taken by the Event Horizon Telescope, zooming way in to the tiniest innermost region of M87, kind of solar system scales in the heart of M87. And what you're seeing is the hot gas careening around the center of the M87, getting pulled around and around and around and around until eventually it falls into the supermassive black hole in the center of the galaxy. And this interaction plays a large role in driving this enormous jet of material that's shooting across the side of M87. Okay, so M87, even if you're not super excited about massive galaxies for themselves, because they're pretty rare, these are the rare beasts. They're actually so big that they make up for how uncommon they are. So if you add up all of the stars in the universe, the majority of them, probably around half, depending on how you do that addition, probably around half of them are in galaxies like this. It's pretty bananas because they're so uncommon. They're big, which means that they host the biggest supermassive black holes, which are pretty cool and exciting. And they're also big, so they're bright. So even if you're not super excited about big galaxies, and you really care about understanding the distribution of stuff in the universe, these are these really bright beacons that can be used to trace cosmology, to trace the distribution of matter in the universe and the growth of that matter. Okay, so I'm going to come back to this cartoon many different times. And I don't expect you to know the details, but I want you to kind of keep one thing in mind. If you want to make a massive galaxy like M87, we think it probably comes in 3 acts. You make all of the stars. Somehow you stop making stars. That's pretty mysterious. We call that quenching. So that's Act 2. And Act 3, you keep growing by eating your neighbors. Okay? And it goes in that order. And because the meeting that I'm here talking about is focusing on the first billion years in the history of the universe, I'm going to focus on Act 1 and a little bit on Act 2 today. Okay. So I am an observer. I use telescopes. But thankfully, I have collaborators, including Deshika, although this is not his movie, who make simulations. So they put in all of the physics that they think is important for making a galaxy, and then they allow that to, they allow the universe to grow and the galaxy to grow inside of it in this little box. And so they make videos like this. Okay, so the center of this simulation will turn into a massive galaxy. The biggest zoom here, the biggest box in this movie, is just an inset of the universe in this simulation. All of the pink and yellow stuff is gas just falling into the center of this gravitational potential well. This very massive, dense thing, largely dominated by mysterious dark matter, but also including the galaxy in the center, that pulls in, just due to gravity, pulls in that gas. The gas swirls around and eventually falls into the galaxy. And there's a zoom out here. You can see the cosmic web feeding this. I'm going to play this again while I talk a little bit. And in the right-hand side, you can see the stars zoomed way in. Okay, so it's galaxy scale, kind of bigger zoomed out galaxy scale, and large scale. Okay, universe is full of gas, but primarily it's getting pulled to the nexus. In the center of this, a big, massive galaxy will form. Now, gas is coming in pretty easily at this stage. Every once in a while, you'll see something that looks like a bomb just blew up. Okay? That's real. It helps to kind of regulate the efficiency of which the gas falls in and fuels the galaxy. By the way, as the gas comes in, the gas will eventually collapse and make stars that you're seeing the galaxy grow in the center. You get this nice swirling disk. You're kind of looking at an edge-on view here. But, you know, as you get clumps of gas that come in, it gets less and less disk-like. So this movie basically focuses on acts 1 and 2. Eventually, you have to get rid of that gas because as you keep bringing in gas, at least the cooler gas, you keep fueling star formation. And we know that somehow that has to happen. The bombs that are exploded in the simulation, those are attributed to the supermassive black holes, but those are generally below the resolution of the actual simulation. So there are some, you know, somewhat simplistic prescriptions that we use to throw that in. And then eventually you have to shut off the star formation. This is an empirical fact, but the details of which we certainly argue about. Okay, Act 3 looks something like this. Now I'm turning off all of the gas and only showing you the stars. Okay, this is a different corner of the universe, but the concept is the same. In the center, you'll make a big, massive galaxy. Over time, this happens because the galaxy in the center, the primary galaxy in the center, in fact, until a little bit later, you don't know which one it is, has neighbors. And eventually, it doesn't. It's like the Borg. It just simulates all the neighbors around it. And it grows. And even if it doesn't start looking like M87, it ends up looking like M87, kind of. Okay. The details of this simulation are almost certainly not right, but the broad strokes should be the backdrop against which you think about the rest of the talk, okay? All right. I am not a simulator. I do not make those models, although I am grateful for the people who do. I'm an observer, so I like to take a telescope. I'll take any telescope you want me to point, ideally the bigger ones. And I look into space. I look into the distant universe. And the reason that that's useful is that that whole process that you just saw in the videos, that takes billions of years. And I am a patient person. Deshika knows I am a patient person, but I am not that patient. So I can't watch it in real time. And instead, I choose to take telescopes, look further and further and further away, thereby looking further and further into the past, right? Because the speed of light is constant. So it just takes time for the photons to get to my telescope and then to get to my computer to analyze them. And you know, the same premise is true. There's nothing special about astrophysical objects except that they're really far away. So of course, I'm looking at all of you in the past. It's just that the speed of light is extremely fast compared to the distance between you and me. The speed of sound is actually less fast, and so that's why you get the echo between thunder and lightning. Anyway, okay, so part 1 of my talk, that was just the introduction. Part 1 of my talk is, and it's kind of the crux of my talk. When did these things form, right? And as part of that, the first part of asking when did they form is how do we actually figure that out? So I actually wanted to spend some time, and it's maybe a little bit pedagogical, but I think it's useful, talking about how we age date a galaxy. And in doing so, tell you why it's so important to actually see this happening, I mean, quote unquote, in real time, but at least in snapshots in real time, as opposed to just trying to kind of infer the full history by looking at M87. Okay, so here are 2 images of collections of stars in our Milky Way galaxy. I never get this kind of spatial resolution, but it's lovely when you can show it. And the one on the left is the Pleiades cluster. You can see this with the naked eye. If you go outside, I'm a really bad observational astronomer, and I don't know if it's up right now. I could check later. But if you go out in the sky in Aspen, you certainly will be able to see this with the naked eye. How many people have seen the Pleiades? It's the cutest little constellation there is. The reason that you can see the Pleiades with the naked eye is because of these behemoth blue stars, right? These are This is a super young cluster very nearby in the Milky Way. And on the right-hand side is a globular cluster. This is an old collection of stars, and these look different. I don't have to play same or different here. These look different. This kind of gets at the heart of how we age date galaxies, but there's one other thing that I wanted to kind of emphasize. All of those faint red stars are there in the Pleiades. When you form big stars, you also form little stars, lots and lots of little stars. You just can't see them because of the giant spotlight in front of them, okay? And so the first live fast and die young is actually the kind of massive stars, the big stars, the bright stars. When you form a bunch of stars, those hide all of the fainter stars, but they disappear pretty quickly. And so when we're age dating galaxies, fundamentally, we're just looking at what has died. For these big stars, these big bright blue stars, they'll explode as supernovae and either end as neutron stars or as black holes. So here's my cartoon. Hopefully, if you didn't understand what I was saying, hopefully the cartoon will make it very, very clear. So I take a cloud of gas and I turn it into stars. I will get very few blue stars, big stars. I'm color coding them by colors, and I'm also making the symbol sizes scale by the mass of the star. I will get some more green stars and many red stars, tiny little stars, okay? If I scale these symbols by how bright they are, though, it looks quite different. You don't see the other stars, basically. I mean, they're there, but mostly what you see is something blue, and that's what you're seeing in the Pleiades cluster. And if I just take this cartoon population of stars and age them over time, in something like a million years, the blue things are there and then they disappear, and you can start to see the green things. And if I wait a little bit longer, I see the red things. Now, here's the problem. The problem is that this happened, the stars get red after about 1 billion years, give or take. These things live forever. They live a really long time, which is good for us because we live around a kind of little star. That's good for us because we don't want our star to explode in 1 million years. We would prefer for the Earth to be protected from that. But it's not great if what you want to do is say something about how old these red stars are. Okay, and if you have a kid, I have a 2-year-old, and so I've seen a lot of these silly growth charts. And the growth charts for humans are really steep, and you can figure out how old somebody is by looking at their weight for a while, and then you hit 20 and they peter off, right? And you probably shouldn't use weight or height to figure out how old somebody is. You have to figure out more subtle clues. Same thing for galaxies. Okay, so I'm going to actually draw you back to this cartoon, and I intentionally made these look wonky. The problem is that M87 is full of red stars. We don't know exactly how old these stars are because you have to look for the little subtle cues. You're not in that kind of steep part of the growth chart. And so we don't know if that cartoon should be super stretched or kind of the history of M87 was more leisurely in general. And basically because we haven't been able to look far enough away to differentiate, to get to that point where we're looking for the difference between green and blue and red stars. We're just always looking at red stars. Okay, so how do we get further? The answer is this glorious diamond-looking thing. This is the last view that we had of the James Webb Space Telescope on Christmas morning of 2021. Dad, my dad is in the audience. Dad, you should earmuff right now. This is the best Christmas present I've ever gotten. So the rest of this talk is going to be like my ode to the James Webb Space Telescope. I'm going to be really explicit about that ode now. So why is it so awesome? Because it is. We just spent the better part of half a week talking about how awesome it is, and I think that in 10 years we're going to keep doing this, knock on wood. Okay, so first of all, JWST is sensitive to a crucial part of the electromagnetic spectrum. for a lot of different things, but I care about distant galaxies, and I'm really excited about Webb because it stretches into the infrared. So I spent a lot of time working on the data from the Hubble Space Telescope early on that mostly focuses on light that we can see with our eyes. But Webb is crucial. And I'll compare it to this. You can see Spitzer. Spitzer is no longer in operation. I'll compare it to Spitzer in a second. The reason it's so exciting to have this sensitivity in the infrared is because as the universe expands, the further and further away I look, the photons have to climb through that expanding universe. And that stretches out their light, making them fainter, tinier, well, to a point. There's a caveat there that I'm not going to get into. Tinier, fainter, and redder, because their light is stretched out to longer and longer wavelengths. And it's lost by the Hubble Space Telescope and captured by the James Webb Space Telescope. It's also got this awesome, beautiful hexagonal mirror that's quite a bit larger, substantially larger than the Hubble Space Telescope mirror. So the power, the collecting power, depends on how big your bucket is. Imagine you're collecting photons. It doesn't depend on the diameter of your bucket. It actually depends on how basically the area of your bucket, how many photons will fall in. Just like collecting raindrops, it's not actually that much different. And so it's about 7 times more powerful than the Hubble Space Telescope. Spitzer was awesome, but tiny. And so it had a full diameter of about this, 0.85 meters. And so it's about 60 times more powerful than the last telescope that was sensitive to the infrared. And there's more, because when you have a bigger aperture, you get higher spatial resolution. And this is, I love this image. I know that there are better images now, but this is the first actual image that scientists who were not part of the commissioning team got to see. So this is not even a science grade image. This is with the alignment camera. But this is the same star going back and forth between Spitzer and this alignment camera. And you could just see all of the blobs in Spitzer turn into distant galaxies. This is not a science image, but it's the first thing we saw. And this, collectively, astronomers breathed a sigh of relief. So this is pretty awesome. This resolution is even harder as you go to longer and longer wavelengths. And so this is something that was really challenging in the past and is really pretty awesome. The last thing that is exciting about Webb is its instrumentation. So Webb has 4 different instruments, and each of them has a whole bunch of different operational modes, all of which are exciting in different ways. The last thing that I'll say, and this gets slightly technical, but I just love spectroscopy, so I'm going to do it. If a picture is worth a million words, or 1,000 words, 1,000 words, a spectrum is worth 1 billion or more, right? I always joke in my group that spectra don't always give you the answer, but it's your best darn chance at getting there. So that's going to be a theme that comes back. And the spectrum is everybody is familiar with spectra, even if you don't know that you're familiar with spectra. So every time that you look at a rainbow in the sky, that's just created because the light is passing through water molecules in the atmosphere and splitting the light as a function of wavelength because of the refractive index. Because the speed of light through the water is slightly different as a function of wavelength. And so you can split it with a prism, like this beautiful image here. You can split it with grating. You can split it with, I don't know, a CD. Do people know what CDs are anymore? Anyway. No, this is not my Intro 101 class. You probably all know what a CD or DVD is. Okay. When we take a spectrum of a galaxy, it looks something like this. I talked really broadly about the colors of stars. The colors of stars show up in basically the shape of your spectrum, the shape of that, we call it the continuum, but the arc of the spectrum. And then you see these features. There are bumps and wiggles that go up, and those correspond to quantum mechanical transitions in the ionized gas that lives inside of usually inside of the galaxy. And then you can get these features here that are absorption features. Those are mostly produced by photons getting absorbed in the atmospheres of stars inside of the galaxies. This is all to say, and how many people have seen ionized gas tubes like this? Where you can see, if you heat up the ionized gas enough, then you can emit photons that correspond to these quantum mechanical transitions. So you can figure out what galaxies are made of using these spectra. You can figure out how quickly they're moving and how far away they are based on where you see these features. So spectra are awesome, and Webb can give them to us. Okay, part 2. You have JWST. Could you please tell us, when did these massive galaxies form? Okay, so I'm going to tell you a little bit of a story. And it's a little bit of a circuitous story. But it starts on July 11th of 2020. And I'm sitting in my office on Zoom, or 2022. I'm sitting in my office in Zoom in part because we were weirdly, slowly coming back from the pandemic, and in part because I work with an international team of folks and we were all excited and wanted to be together, so we almost were together. I apparently have the same water bottle that I was drinking from, but it's seen some things since then, which I probably have seen some things since then. So we were all just waiting to see this image, and I certainly hadn't seen this image before it came up on my screen. Along with this image, actually 2 days later, there was a collection of early release data that was released to the public, and I was obsessed with Calvin and Hobbes as a child, hardcore obsessed, and this captures the next year. The good, the bad, and the ugly. Okay, so what do we learn initially about massive galaxies? Well, we thought we learned really quickly something about massive galaxies. So we started looking through these early data, and we started finding these things that were super red. We were already primed to look for these super red things. And they looked pretty weird. Well, not weird, actually. We would have expected them if they were much closer to us, but they were further than we expected. And we started playing with the models, our familiar models, to try to interpret what they looked like. I mean, they look like these little red dots, which of course is what we ended up calling them later. But they're not that exciting to look at. But once you start to model them, we got some really confusing results. Basically, here's a plot from one of the first papers. If you just model the light from these galaxies using the models that you would get from a slightly more sophisticated model than my cartoon stellar population, you find that these things are so bright that at the distances where we detect them, the universe is about 5 million years old at that time, about 3% of its current age. They're so bright that they should already have as many stars as the Milky Way, at 3% of the age of the universe. And the press noticed. My physics colleagues noticed. My physics colleagues were worried that we had broken the universe. How many people remember seeing this explosion of, astronomers found really massive, really early universe-breaking galaxies? Few people. Okay. I mean, we knew this was a little bit bananas. I will say that I'm not sure we knew how bananas it was. So if we had really pushed this on the theory side, you can go to the growth of dark matter, which we actually think we understand very well. Dark matter just grows by gravity, twiddle by gravity. And so we have a really good sense of how it should grow over cosmic time. And so you can ask the theorists, how crazy is it to make something the size of the Milky Way at 3% of the age of the universe, based on how quickly you could maximally grow a galaxy? And it took about a week for Mike Boyle and Kulchin to tell us that either we were totally off our rockers, or we had to change our cosmological model. I can be a little bit more specific about that. The biggest uncertainty here, we had a pretty good idea of how far away these things were. So the biggest uncertainty is how we took those images and added up how much light we saw and turned it into how much mass we were seeing, right? So the models that we used to convert light into mass were either totally wrong, or our standard cosmological model had to be wrong, and not just a little bit wrong. If you took all of the available normal matter, baryonic matter, and turned it into stars, you still could not make galaxies this quickly. Okay, well, as always, the spectra can't give you the answer, but they give you your best chance. And for those with eagle eyes, this is a spectrum of one of those initially thought to be massive galaxies. And what you don't see is that nice curve that you would get from the stars, right? And this is a little bit of an oversimplification. This is one of the more cut and dry examples. But this, when you take a spectrum of this is unambiguously not something you should model with stars. This is unambiguously light from a supermassive black hole. And there are some other examples that are less unambiguous, but it has over and over and over been the case that when we take a spectrum of the things that we just saw those little postage stamps of, the stellar models were failing us. Now, I'll tell you that we spent all of Tuesday arguing what models we should be using to convert the light into mass, not just for images, but for spectra. So we don't know as a field what the right model is, but we know what the wrong model is. So cross that off. We haven't found any massive galaxies that are breaking cosmology. Okay. The other thing that I just wanted to point out that these are plots just from the first year of JWST. JWST has fundamentally changed our horizon, okay? The frontiers, where we're not seeing light anymore, have gone way further. So this on the left-hand side is galaxies, and on the right-hand side is black holes. This is just in the first year. The things that we knew about before JWST in the galaxy side are here. This is distance in this direction, time since the Big Bang on this side, and then cosmological redshift, if you like thinking about that term. But the red points, which are the things that we've spectroscopically we've confirmed with JWST, push to much greater distances. And I've plotted them by how bright they are. So we've collected a much more representative, much fainter collection of galaxies, not just the tip of the iceberg that we had prior to JWST. And the same thing is the case for supermassive black holes, right? So we're finding fainter things and we're pushing them to larger distances. Okay, so you promised that you would tell me, I promised that I would tell you about massive galaxies, so I'm gonna come back. Just a reminder, this is what the spectrum of a massive galaxy is, so you can use this to tell you about how old a galaxy is or what it's made out of. And these are pre-JWST. We were totally able to do this for distant galaxies. They just weren't that distant, and it was deeply painful. So using the largest telescopes in the world, it took something like 20 hours to take a spectrum that looked like this, and it wasn't, this is looking back maybe half the age of the universe, but there's so much here that's important. And here, these are slightly further away. Let me take a second and just be really explicit. So here I'm plotting the age of the universe on the top, and redshift if you like thinking about that. This was super painful. I'll remind you, these telescopes are on Earth, so you can only observe at night. So this is not like I sit down for 20 hours and observe this. This is spread over long periods of time. This project took a total of a full year on one of the largest telescopes in the world. Anyway, JWST, total game changer. Let me tell you about how things lie on this timeline now. So these are, and everything that I'm showing you is a super robust example of what I would happily call a massive galaxy on this timeline. Okay, so JWST quickly showed us relics of a very early formation history based on the ages. So you can take a spectrum like this, you can model it, and you get a sense of how old it is. The longer this bar, the more uncertain it is, okay? So this isn't uncomfortable, right? It's 2 billion years, but this is a really long bar. So, maybe something like this could form pretty early. This is an uncomfortable example. The bar there, this is a galaxy that we see when the universe was about 2 billion years old. And if you take a spectrum, I'll show you a better spectrum in a second. If you take a spectrum of this and you figure out how old it is, it's 2 billion years old. But cosmology sets that hard upper limit. So we would call this like a maximally old solution. That's a fairly long error, a fairly long band. So maybe it's got some uncertainty there. But this is getting pretty close to forming as early as it could form. One secret is that one of these, this object is actually the same object that I showed you before, but here are some other examples pushing further and further into the distance and pretty close to that uncomfortable point where you're forming galaxies as soon as they could form. Here's another one. And probably the most distant thing that I would call a massive galaxy. Pushing pretty far up to the theoretical limit. Okay. If I sum this up and stop showing you spectra, I promise I'll show you some images too, and just plot the number of these massive galaxies, and as a function of how far I'm looking back into the past, or redshift. This is what we knew before JWST. These are the theoretical models. Turn the knobs, do anything that you can to make a realistic population of galaxies. And this is what we're finding with JWST. And I'm not just plotting what I would call the linear number. I'm plotting this in a log scale. So this distance right here, that's a factor of 10. This distance right here is a factor of 100. We're seeing over 10 times the number of these relics than any of the models can currently produce. Do I think that this is lasting? No. Do I think that we have to go to the drawing board a little bit? Probably. But I'm not super surprised by that. Okay. This is just my counting exercise. And I thought that what I would do for the last little bit of this talk is give you a highlight reel of the other things that we've been able to do with this magnificent telescope. Okay, so that's part 3. What else have we started to learn beyond just counting and finding way too many of them? And the last concept that I wanted to introduce is the concept of gravitational lensing. Because sometimes we're greedy. And sometimes we want to see even fainter things and at even higher resolution than can be provided by the James Webb Space Telescope, because we're greedy. And luckily, gravitational lensing provides this opportunity. So basically, gravitational lensing exploits the fact that general relativity says that if you have a massive object, it's not going to pull on things due to a gravitational force. It actually pulls on things because it warps space-time around it. Okay, so in this cartoon, there's a massive blob, which you can't really see, but it's a massive blob that's warping space-time. And light no longer travels in straight paths when space-time is warped. Light travels on the shortest path through space-time. Now, space-time is normal, then that's a straight line. But if it's unintuitively warped by some massive object, it gets bent. And therefore, you don't just pass right by, you pass around, okay? And what this does is shown in this visual. If you look at things that are behind some very, very massive object, sometimes if the alignment is just right, you stretch their images. And they get brighter, and you get much higher resolution. And sometimes you see them more than once. Okay, so I'm involved with a bunch of different projects with Webb, but in the first cycle, I was primarily involved with this project called Uncover, which is a tortured acronym that I'm not going to say out loud. Uncover was targeting, well, nominally targeting this cluster of galaxies. So this is a big collection. Many of these things that are in whitish are actually massive galaxies in their own right. They're just relatively nearby, but they're really large. And they warp space-time, and the real target are the red things that are in the background. And I'm just going to spend, and this is a pretty small patch of the sky. This is about 10%, 15% of the sky, size of the full moon on the sky. So it's really tiny. We've pointed at this patch of the sky with HST, and JWST blows it out of the water, in addition to just probing different wavelengths. I'm just going to spend a little bit of time like bopping around through this image. So you see galaxies that are interacting with each other in the cluster. You see lots of these lensed galaxies in the background. For example, when you see two things that look like they might be mirror images, they actually are. And really everywhere, including in these kind of understudied parts of the cluster, you see these huge arcs. You see lots of little dots. Most of these dots are actually globular clusters, like the globular cluster that I showed you at the beginning, but they're point sources because they're so tiny. They're globular clusters around these massive galaxies in the cluster itself. And there are lensed galaxies everywhere. And there is no way, I would need like 4 different talks to give you highlights from this study, from this survey. We've used these data to death. Other groups have used these data to death. It's been a privilege to run this, to PI this program. One of the cool things that we found was a triply imaged, 3 images of the same thing. One of these universe-breaking things that we at least initially thought were galaxies, but we think are these weird little red dot, probably supermassive black holes. And we took a comically deep spectrum because we took spectra of each of these different images and added them together. If you look at some of the lensed galaxies, this is a massive galaxy that we find in our image, and you look around it, we actually see some more of these globular clusters. Remember that old example that I saw, just tiny because we're so far away? We think we're seeing them in formation, which has been, because they're so old, they're extremely hard to age date. We're now being able to start to see this. And in more extreme examples of gravitational lensing, you can start to see inside of galaxies. This is just one galaxy. And you can see it has all clumps of all different colors. So galaxies themselves aren't uniform, and you can start to see them in the building blocks scales of those galaxies. Okay, I want to say, I think, 2 more little highlights that I think were really cool, unambiguous results. The first one is that if you look at Act 2, the thing that comes out of Act 2, that I would call this the end of star formation. That's also the beginning of building an M87, building something that looks like an elliptical galaxy. So the things that come out of here, you can study the relative motion of one side of the galaxy versus the other side of the galaxy. One side will be moving towards you and one side away. And it's like a frisbee that's rotating. We can see hints that these galaxies, even though their stars look more like an M87, their structures look more like a Milky Way. And I am not involved in this study, but I just think it's the coolest thing. So here's another one of these massive galaxies that's strongly gravitationally lensed. And if you just look at how quickly stars are moving across the galaxy, those are the data points in black. And you can actually see in the center, there are two lines here. One of these models has no supermassive black hole, and the other model has a supermassive black hole. And basically, stars in the very center are moving too quickly to just be due to the regular matter. So you basically can rule out a model without a supermassive black hole in this, which is just awesome. Okay, so I have 2 more slides. And I'm just going to go through and talk about this timeline and give you a couple of summary points, even though I only focused on 1 and 2. Number 1, galaxies form. Massive galaxies form much faster than we thought that they would. They form earlier, more efficiently, and more frequently than models can currently explain, or certainly than models predicted prior to JWST. And we almost certainly are not breaking the cosmological model. Okay, Act 2, galaxies shut off. Similarly, they live fast, they die young. They shut off earlier than we thought that they would, earlier and more efficiently than simulations predict or can currently explain, but almost certainly we'll get there. But the statistics and doing this right will take some time. And then Act 3, which I didn't talk about, but is near and dear to my heart, because previously that's what we had access to. That's not the end of the story, and the galaxy have to continue to build up M87 like structures, and they do that by cannibalizing is a little bit aggressive, maybe like assimilating all of the material around them. Okay, I have one last slide, and I'll just say this. Number 1, science is done by people. And I am unbelievably privileged to work with the awesome group of folks in my group, to mentor them and to work with them, and to work with the collaborators that I have across the world. It's a privilege. Number 2, JWST is awesome. I am so grateful to be working in this field at this time. And it's because of all of you. It's because of the taxpayers. So I am so grateful for that. Thank you. It's really important, and I appreciate it. And the people appreciate it. And number 3, because I think it's sometimes useful to have like a concrete reminder of how old JWST is, that's Otis. He's not exactly the same age as JWST. He's about almost exactly a year younger than Uncover. That's pretty young. We're figuring this nonsense out. We're still, and we're going to continue to do so, knock on wood, because hopefully the JWST will last for another decade. So stay tuned and enjoy the ride. And I'm happy to take any questions.
Yeah, we've got time for a number of questions. In the back.
Yeah, I was wondering.
Marisa will bring you up microphones.
I can repeat, yeah.
During the quenching stage,
Yeah.
do we know that they're not merging with other galaxies during that stage, or can they still be merging with that galaxy while they're still producing stars?
Yeah, so the question is, how distinct are the different stages? Like, are things quenching while they're also merging? And the answer, as you probably saw in the simulations, is absolutely all of this stuff is a total mess in the simulations and probably in actuality. And in fact, there are some models that suggest that the merging is an important part of fueling the burst of star formation that happens before they shut off. So it may not just be a kind of chance simultaneity. It may actually be that there's some causality in there. Yeah, certainly for some cases, but it may be the case that for the general population, that's true. That's a great question.
Does every galaxy have a different gravity or
Yeah.
gravitational pull?
Yeah, great question. Yes. So the question is, does every galaxy have a different gravity or gravitational pull? And the answer is, I mean, you can find two that are very similar, right? But it's a huge spectrum. And the gravitational pull is actually primarily set by the dark matter, because there's so much more dark matter than there is normal matter, like, a factor of 20-ish. And so there's a huge range of, we call them dark matter halos, but they're basically just the quasi-spherical collections of dark matter, the inside of which galaxies form and live. But there's a huge spectrum. And the galaxies that I was mostly focused on in this talk are at the high end of that spectrum. They have the strongest gravitational pull. But there's a huge range all the way down to dark matter halos that don't have galaxies in them at all. I can also repeat it.
I think they want it for the YouTube.
Oh, good, yeah.
Yeah, so when you're looking at the spectrum of distant galaxies and inferring their age from the redshift, how do you tell the difference between a spectral line that's been redshifted from just some other spectral line? Like, how many known lines all need to be shifted by the same amount before you can infer with high confidence that, it's a certain redshift?
That is such an awesome question. That is such an awesome question. So the question was, how do you know when you see a line that it is the line that you think that it is, right, intrinsically as it was emitted? Or do you need to have collections of lines? And the short answer is, please have collections of lines, right? And sometimes you have to make a best guess. But in the ideal scenario, you look at, you know what the ratios of wavelengths should be, basically. And so you look for either pairs or ideally like 3 different lines that you can see, or more. There are some lines that always come together. And so there, for example, are surveys that are focused on studying the distribution of galaxies to study cosmology. And those ones will often focus on those like pairs of lines, because if you catch one, you always catch the other. And so that's like a familiar pattern to look for. But yeah, you always want to look for a pattern, otherwise you'll have an ambiguous answer. Awesome question.
Using the redshift, doesn't that assume that the universe is continuing to expand at a constant rate? And hasn't there been some debate whether or not that is true? In which case that might upset your age determinations.
Yes, excellent question. Awesome. You guys are killing it. So the question is, if you're using the redshift, that's something that you just measure. That's literally, it is how much are the wavelengths stretched, how much are they shifted to the red. So that's something that we measure, but then you're inferring a whole bunch of things about ages and times that depend on how the universe expanded, the universal expansion history. And the answer is yeah. So we make a measurement, and then we assume a cosmological model to translate that into a distance or a time, or there are lots of different versions of distances when you have an expanding universe. But there always depends on your assumed cosmological model. Now, we have a pretty good handle on the best fitting cosmological model, but in the details, there's still some tension between cosmological models that are fixed by the cosmic microwave background at very early times and those that are measured at very late times. So that whole expansion history, it matters, and it will be a kind of systematic measurement uncertainty on any of the physical quantities that we measure. It's a great question.
Hey, I'm familiar with looking at the spectrum through a prism, but when you're in infrared and the higher wavelengths, what do you use for a prism to see that?
Honestly, it depends. Oh, the question is, what do you use in the infrared to split the light, right? And the answer is, actually, most of we call them dispersive elements, right? So a prism or a grating. Most of those are actually very similar in the infrared. It's a little bit different if you get to something like X-rays, but in the infrared, so actually one of the most used instrumental modes of the near-spec spectrograph on Webb just uses a prism. So it's exactly what you'd be familiar with. And then if you want what we would say like a higher resolution spectrum, then you start using gratings. But it's actually those physical elements are really similar to what you're familiar with. Yeah, it's different at very, very different parts of the electromagnetic spectrum, but you don't see it, but it works in a very familiar way. The detectors are a little different, but that's the same.
There's one up front. All the way. And just looking at the time, maybe this will be the last question.
We've been talking about how you measure the distance, but what about what we're measuring? The gases, the hydrogen, the helium. How has that changed? And why did?
Yeah, so the question is, I mostly focused on how we're measuring things, but the question is, how are the compositions different at earlier times, right? How, like the relative, you mentioned hydrogen and helium, and there's been a lot of work that's been looking at what I would call the chemical abundances, but really just how much of any element is inside of a galaxy at any point in time. And we think that that's important because the universe starts as mostly hydrogen and helium after the Big Bang. And then it's the stars that enrich us. This is, we are made out of star stuff because we are made out of the heavier elements that are spewed out by previous generation of stars. So that has to happen at some point. And as you look further and further back, you do see indications that there has been less kind of chemical enrichment. But the curious thing is that in the massive galaxies, you can actually tell, number one, that they've, that the chemicals that you see inside of them also reflect those extremely rapid and extremely early star formation histories. So they're actually very enriched very early. But I would say it's pretty early days, and there are some kind of, without going too deep in the weeds, we have certainly found differences in the types of chemical abundance patterns that we see in very distant galaxies. Yeah, great question.
All right, thank you. Would you join me in thanking Rachel once again?